Okay, I think it should be working now. Okay, we
it's
we are
now
already we are already past 5, so
open.
um, I can start. Um, Today we're going through one of my most recent uh, articles with Nora. This is I would say, a mostly negative results kind of paper, and it's also short enough. So if we have time, um, depending on if there's questions and discussion, I have another short one on the next tab, which is also ours, which is slightly more positive results. But it's even shorter than this one. So if we have time, we go through it. So the inspiration for this work, like, is the idea that if you add a perfect natural language explanation of a model, you could potentially rewrite it in some way with your natural language explanation, and hopefully you'd get back the same behavior of the model. So if your explanation was faithful, you should be able to do this. And the idea in particular that we were trying to achieve was, okay, let's take a sparse autoencoder. In this case, we actually used a transcoder, but it doesn't actually change the specifics. Let's take a sparse autoencoder. Let's try to do autointerp on all the latents of the sparse autoencoder. And then let's replace the encoder with the explanations, and then a language model that is given the explanations, the current token, and is asked, okay, should this latent be active on this token given this explanation? Then the LLM says yes or no, or we actually ask it to give a number or to know how high the activation should be. And then we use this number to decide which decoder directions of the sparse autoencoder to use. I think there isn't a picture, so I cannot show you a picture. There is a picture. Yeah, so we first start by going through all the latents of our SAE, or in this case transcoder. We collect activations. If you're familiar with autointerp already, I'm just going to repeat it for a bit. If you're not, you can also check our other paper on this, or the original sources, like the Anthropic paper or Bills et al. for neurons. But the idea is that you collect activations of your sparse model. Then you sample these activations in some way to make these examples. Here, these are real examples of a latent that I found. Just for space reasons, I cut it very short. But then the explanation that the LLM gives for this kind of examples is verbs denoting directional movement or change. Also, this explanation is a bit, I trimmed it a bit too for space, but this is the general gist of it. And you do this for all latents of your SAE. In this case, our SAE had 32,000 latents. And as I said, you show this is the sentence that you're trying to pass through the model. The last token of the sentence is class. And you ask the model, okay, if the latent explanation is verbs denoting directional movement or change, what should be the activation? And the model says 0. But if you instead say, okay, the explanation is references to classes of people, the model says that the activation is 2. It's 2 and not a higher number. The activation goes from 0 to 10. It's 2 and not a higher number because this class doesn't seem to be about classes of people, but maybe data classes or something about programming. Then you take all these activations that the model predicted. You once again do top k. I mean, you do top k over this, so you get 32 activation numbers. And then you look at all your latents, the directions of the decoder, and you make a reconstructed vector, which you put back into the residual stream. Because in this case, we are doing a transcoder, we skip over the MLP. So instead of the output of the MLP having an SAE, it's the input of the MLP that has the transcoder, and then we write directly to the residual stream, and we don't use the output of the MLP. When I say that this is a partially or mostly negative result paper, is because if you do this process like I mentioned, both the explanations and this kind of simulating process are uncalibrated, very much so. So if you see this is over 10,000 different prompts, looking at just the last token of that prompt. The actual value of the activation of that latent is this blue histogram, which you can see here. This is the activation distribution and normalized. You see that it has this like exponential tail, and then here at 0, at exactly 0, it has a huge peak, which is the majority of activations are 0, because this is a sparse. It's a transcoder, a sparse transcoder. So most of the activations are going to be 0. But you can see that the predicted activations by our LLM are several orders of magnitude higher on the activation part. And so here on the non-activation part, it looks like it's a small gap, and the gap is small because it correctly identifies, like 90% of the times it correctly identifies that the latent is not active. But by incorrectly identifying that the latent is active on 10% of the times, it over-predicts by a huge amount the distribution of activations. So this is not for a single latent, this is in general, but because this is the distribution, you can assume that if we were to look at individual latent predictions, they will look bad as well. To try to fix this issue, we do something called quartile normalization, where we basically, there's a description for this here. We basically take the empirical cumulative distribution function of the activations, and the distribution, the same for the normalized activations, and we are trying to we do some operations such that at the end, so we transform the normalized, the predicted activations such that these two distributions should match at the end, which is what you see. So we go from this orange curve to this other orange curve, where now the normalized activations are much closer to the activations. One important thing here is that...
sorry, I missed it. Can you go over it again?
Yeah, so we explain the process of quantile normalization here a bit in detail. I think I'm going to just end wave my way through, but this is quantile normalization is a transformation that you do to your data that has a given distribution, and you try to transport it to another distribution. So in this case, we are just, it's like we are shifting, like multiplying all the activations by a certain value, depending on the value of the activation, such that at the end, you go from a distribution that looks like this orange one. The target distribution was this blue one, but we got this bump here because instead of cheating, instead of doing this transformation using the real data and the real activations, we use the distribution computed separately from these real activations. So we didn't have access to the ground truth. We just had access to the empirical distribution over another data set. And because of this mismatch, the transformation doesn't exactly make these two on top of each other, but it very closely matches. So you see that before there were several orders of magnitude more predictions of activations of, let's say, value 5. So you see 10 to the 6, and the correct number is closer to 10 to the 2, so 4 orders of magnitude higher. And then we go back to, it's still 1 order of magnitude higher, but for most of the distribution, we get, let's say, calibrated prediction. Again, it's important to note that we are not using the ground truth to push each activation to the correct number. We are just saying, okay, our predictor is very uncalibrated. We know what the distribution, the empirical distribution should be. Let's try to push down the values that it predicts, such that they match closer to the real distribution. This mostly means that a lot of these values just go pushed back to 0 and are set to 0. I don't know if you want me to try to explain it again.
Yeah, I kind of find it like, isn't this similar to how you see the answer on a test and you correct the previous answers to be similar to the test results? Because we have to look at the...
Not exactly. So, not exactly. Imagine using this test thing. Let's say that, and yeah, I think I can make an analogy there. Let's say that you make an exam, and it's just a ABCD exam, and at the end of the day, you predicted A 80% of the time, B 10% of the time, C 5% of the time, and D also 5% of the time. The actual distribution of the correct answers are known. I know them, and let's say that they were 25% each. What here we are doing is we are shifting some of the A's, let's say, to be B's, C's, and D's, such that at the end the distribution matches, but we don't know if the A was correct or not, and we don't know if the B was correct or not. We are just making the distribution closer to the real and underlying distribution. In this case, I'm not even measuring the fraction of A, B's, C's, and D's on the real test that you took. I'm measuring it on all the possible, not on the possible, but let's imagine I'm measuring it on a different schools tests that uses the same distribution than mine. Like mine is sampled from from all schools, but I don't have any way of actually cheating on the distribution because it's not. I'm not taking the ground truth distribution. If I was taking the ground truth distribution, this blue and orange would be the same. Still, this is cheating. I mean, you wouldn't want to have to do this calibration process. Hopefully, you'd have both a calibrated model, and your explanations would be good enough that you wouldn't have to do this, let's say, reshuffling. But it is not the case. Like the point of this paper is to say, okay, if you don't do this, it doesn't work at all. So let's see what happens if you do this. And the answer is that it still doesn't work that well, but it's a bit better.
And these activations come from using like encoders on the on the previous activations and putting them in the residual streams.
Yeah. So these activations. These the blue activations are the encoder activations over 10,000 prompts only on a single token. Let's say the last token of that prompt. While the distribution that we use to normalize it is over 10 million tokens collected everywhere from the distribution. And so it's a much larger distribution. Mm-hmm. Yeah, and so what are the results of this? So in the perfect world, you'd be able to do this, and you'd get a model that behaves similarly to a model where you didn't do this intervention. Sadly, we barely get better results than completely zeroing out the MLP. So here we are measuring the cross entropy increase by doing this operation. Just by adding the transcoder or just by adding an SAE to the model, the cross entropy loss of the model increases. It increases less for the transcoder than it does for the SAE, but both of these, you can imagine that it's like you're training. These increases are significant enough that it's like you're training the model on only 20% of the compute that you use to train the model. So we do these experiments on Pythia, small Pythia, on Pythia 160 million, and these values of increase of absolute loss are equivalent to an earlier checkpoint of Pythia, where it was only trained for 20% of the data. And so adding SAEs or transcoders already ups the performance significantly, but then trying to do this rewriting with natural language obviously hurts the performance more. And unfortunately, at the time of writing, our explanations are not good enough that you can actually rewrite the model. It would be better to always say, okay, this MLP doesn't work, And so you'd set the MLP to 0, and doing that would always be better than predicting. You can see that the green lines, the green bars, are ever so slightly smaller than zeroing out, but the error bars are big enough that we are not we are not willing to say that this works.
So I have a question. Why is the sample? Oh, because at 100%, there is no sampling. You're taking everything. Another question is, am I reading this right? That the absolute CE difference, like the cross entropy difference, with 100% of the latent substituted, is better than the SAE for a transcoder?
For a transcoder. So, so an SAE, just a normal SAE, increases the loss so much. At least this one that we trained. I'm not saying that this is all SAEs, but this is an SAE. Right. The SAE with this given size, with this given K, increased the loss higher than if you set the MLP as this is a residual on the left. On the left is a transcoder on the MLP. On the right is a residual stream SAE. So
okay.
You can't compare them side to side. And that's why when you zero out the SAE, you see that the number that like the 100% on the right plot is much higher than the 100% on the left plot, because it's much worse to zero out the residual stream than it is to zero out a single MLP. I was going to explain what the fractions mean. So you can do this rewriting part on only a certain part of the transcoder. So the transcoder has 32,000 latents, but you can decide, okay, I'm going to rewrite 1% of the encoder, and I'm going to use the rest of the encoder normally. So I'm just running it. I'm collecting the activations, and then I'm seeing the activations that my LLM predicts. I'm doing the transformation that I mentioned. We do top K again, and then we decide which latents to select as active. And you can do this selection of the fraction of latents to substitute in two different ways. One way is that you just randomly select what latents you want to substitute. The other way, which is clearly better, is that you just substitute the latents that you're the most certain about the explanations. So we, independently from this procedure here, we generate a score for the explanation of each latent, and then we are able to rank. So let's say latent 0 has a score of 80%, and then latent 1 has a score of 91%. We can make a list from that orders these scores, and when we select 1%, we select just the top 1% of latents. And we see that, especially when we're sampling a big part of latents, sampling the best ones is much better than randomly sampling. This is averaged on this side over 10,000 prompts, and on this side only over 1,000 prompts, because this is very expensive. You have to think that not only do you have to generate the explanation for each of the latents, so for the 32,000 latents, for each of the prompts, you have to prompt an LLM and ask it, is this latent active or not? So for 10,000 prompts, we have to do this procedure 10,000 times 32,000 latents, which is like, is it 30 million? 300 million? Yeah, it's a big number, and so this process is expensive, but we are still not at the point where we are confident that our explanations are good enough that you'd be able to rewrite the transformer.
And the
Instead,
sorry,
yeah,
one
go.
more. The error bars are SEM, or they're not confidence intervals, right? There's something else.
Yeah, they are confidence intervals, but of the median, because so they're.
So you can have over. So what? I guess what percentage of confident? It's not like 90% confident.
It's 95.
Okay, so
It's
you
95.
can have. Okay, so you can have error bar overlap with 95% confidence, not for like the small ones, but for the like 80% or even the 60%.
Yeah, so we are very close, and in fact, we didn't add this to the paper because I genuinely think that that's really pushing the bar. But if we do this normalization with the real distribution of activations, instead of sampling from the tests of all schools, let's say, we are lower than zeroing out. Again, we are still not cheating. I'm not going over the first question of the exam and seeing that my number is A and that the correct one is B, and so changing A to B. I'm just seeing that I have too many A's and I change some of the A's to B's. In this case of a discontinuous distribution, it doesn't work that well because it's not obvious which A's you choose. When it is a continuous distribution, you just move all the A's that are closer to B's to B's. And if you do that using the real underlying distribution, we are better than zeroing out. But we believe that that's too much shit. Like you have to know the real answer,
Right?
And potentially you'd not want to do that.
What about this discrepancy? So randomly sampling seems to do worse than zeroing out for.
Yeah. So we are still randomly sampling. We are still doing the rewriting. It's just that you choose randomly which latent to rewrite, and it seems like zeroing out is very it's just that zeroing out is very competitive, and in fact it's better than sampling.
Right.
Just random.
So it's almost better. Like if you, yeah, it's almost better if you give like no information than if you give random information.
So again, it's not random information. It's if we select 32 random directions every time, the absolute C difference would be on the order of nuts of 1.
Okay.
So if you randomly selected which latent to be active, the bar would be off the charts. That's not what sampling means. So sampling, you're still trying to correctly predict if the activation is right or wrong. It's just that you're not selecting the best explanations. Some of these latents have bad explanations, and you're still trying to explain them. So we know that these explanations, because of the scores that we have, we know that these explanations are not the correct explanations because the scores are too bad. But we are still using them to predict just because we don't have better explanations. Like the purpose of this pipeline was to make everything to be automatic. I'm not sure. Yeah. Still, the results are not completely negative because these scores that we are computing on a different set of prompts, on a different set, like on a completely different task, let's say, to evaluate if explanations are good or not, are predictive of this specific task. So the higher your score, the better your explanation works on this task. And in fact, if your score is closer to 1, which is the maximum score, your explanation is always going to be both more sensitive and more specific. The reason why being specific matters, and that's, if you notice in this plot, we have a log scale that goes from 50% to 99.99%. Is because if you're thinking about a normal sparse autoencoder or a transcoder that has 32,000 latents. Let me see where I did this. If your SE has 32,000 latents, which is a normal size for a small model, but you can imagine that, for instance, the SAEs that we trained for Llama have 131,000 latents, so close to 5 times this. And if you have a specificity of only 99%, you're still going to predict that 32,000 latents should be active. But because we are using K of 32, meaning that this SAE only has 32 active latents at any given time, this means that you have 10 times more wrong predictions than you can possibly have correct predictions. So even if you have a specificity of 100%, meaning that you get this 32 correct, you're still predicting 320 other as active. And now you have to decide from these 350 latents which ones of them are active, which obviously will make you, even if you have a specificity of 100%, at the end of the day, you'll have less than 100% because you have to select from these 350 only 32. In the real, let's say, in the real world, our explanations normally only have a specificity of 85 to 90%, which is, again, 1 order of magnitude worse than you need. So you'd predict 3,200 active latents when only 32 are active. And this means that even if you're very good at predicting which actives are active, those are going to be drowned out in the noise of your predictions. And I think the biggest takeaway from this article, if there is one, is that we really have to strive to make explanations as specific as you can, and yeah, it doesn't only matter that your explanation can correctly predict that the latent is active or not. It should also be able to predict when it is not active, and it's much more important to predict when it's not active than it is to predict when it is active, just because of how infrequent it is. If you want to do something like this, so if you want to do a partial rewriting, because you have to predict the activations for all latents, it's much more important that your explanations are specific, because you don't want to overwhelm your system with false positives. I'm going to leave this one here. If people have any questions.
I had you until the last part. I just want to make sure. So sensitivity is the true positive rate, right? And specificity is the true negative?
Yes.
Okay.
Yes. And again, I think this is important because most ways that people try to do auto-interp and evaluate auto-interp results is by looking at how well the explanations match with activating examples. But they rarely check if this explanation will lead to a high number of false positives. And with a high number of false positives, you're never going to be able to do this kind of rewriting, just because, again, there's many more opportunities to make a false positive just because of the class imbalance than there is to make a false negative. Yeah, I mean, we are at 41. I might as well, if there's no other questions, just because.
Yeah, no, I'm actually more excited about the second paper. Not to poop this, because this is also exciting, but.
Yeah, so one thing that I didn't say about this one is that we are not using a normal transcoder. We are using something which we call a skip transcoder, which is just a normal transcoder. What is the equation? It's just a normal transcoder here with these with a skip connection, because we are doing a transcoder and not a sparse autoencoder. You can add a skip connection. If you're doing a sparse autoencoder, as the skip connection would ruin your thing, because the SAE could just learn this to be 0 and this to be the identity, and you'd have perfect reconstruction. Because here you're trying to go over the MLP. It doesn't. This will not happen because the MLP is not the identity. And adding a skip connection significantly improves the reconstruction loss. And if you when doing interpretability, if you ignore the skip connection, so if you just look at the normal transcoder part, you get the same level of interpretability as if you're just doing a normal transcoder. And then if you'd want to, you can still do interpretability on this connection, which the great thing about this is that it's just a linear transformation of the input. There's no non-linearity. So even if you're doing more complicated stuff like circuit analysis, you'll know how to use this because it's just a linear transformation. So there's no problem of adding it here in the case of the skip transcoder. And so what did we do? We trained a normal SAEs, again top K SAEs, sparse transcoders and sparse skip transcoders on PITIA 160M, and also on Llama and Gemma, Llama 1B and Gemma 2B. We do let's say the normal procedure to train top KSAs using mean squared error as a loss function. We trained 3 different values of K, so 32, 64, and 128, and all the SAEs were trained on at least 8 billion tokens. On the case of PITIA, they were trained on the pile, and on the case of both Gemma and Llama, they were trained on Heta Gemma v2. Um, I'm going to, yeah, for those that are not familiar with our interpretability, like auto interpretability framework, instead, the two scores that we give explanations, we call them detection and fuzzing. Detection is a very simple task. You basically have the explanation, have a set of sentences, and you ask a language model, okay, given this explanation, in which of these sentences should the latent be active? This is very similar to the previous paper. And this is also a very easy test. Obviously, this is a much less precise measurement of how good an explanation is than, for instance, simulation, where you ask the model to predict the activation of the latent or multiple tokens. But because activations are so sparse, simulation gives you a very low amount of signal in terms of diversity of prompts. You cannot check a lot of prompts because you have to do simulation on all tokens of the prompt. While with detection, you can try to sample a whole, like a big range of different kinds of prompts. And hopefully, even though it is less sensitive, you'd be able to evaluate over more prompts and get a good result as well. Fuzzing is like the harder or maybe not version of detection, where you again take the explanation for the latent, and you give the model a list of sentences where some of the tokens of the sentences are highlighted. So we just put angle brackets around those tokens, and then we ask the model if these highlighted tokens should be active or not. Fuzzing is like a simpler version than simulation. In simulation, the model is asked to output a value of an activation value for each token. Here we just ask it, okay, in these tokens, should the value be different from 0 or not? Again, the good thing is that it's much cheaper than simulation, and you can do many more prompts. And so even though it's easier than simulation, you hopefully still get some signal about how good explanations are. This plot on the left just shows the distribution, the overall distribution over, I think, 500 different latents of both SAE, a skip transcoder, and transcoder of PITIA. And you see that the average score of the PTSAE is much lower than the average score of both the skip transcoder and the normal transcoder, both on detection and fuzzing.
About the difference between the skip and the regular transcoder.
Yeah.
Did you guys do try to do some analysis on like the difference of the distributions, like if they are different?
Do you mean like the distribution of scores?
Yeah.
Yeah. We didn't do like a full detailed analysis. They seem to be very similar. And you'll see here, where is it? It's above. What is it? You see that the auto interp scores of transcoders and of skip transcoders especially for the larger sizes, are very much the same, if not even a bit higher. So you see this square and this square is higher. It's the transcoder, and this blue circle and this circle is higher as well. But it's not Pareto better because the skip transcoder just has a less degradation of the model performance. This is missing a percentage sign. So we didn't exactly look to see if the distributions are the same. I don't think it matters that much. In general, what we care about, I think, would be to have your point the closest to this corner, and when that is not possible, I think this other plot, which is for me also very important, which shows how good the explanation explains the different parts of the distribution. So here is the accuracy on examples that are sampled from the highest quantiles of activations, and you see for all the models, the accuracy on these prompts is higher than as you go down and down to almost non-activating. You see that in the case of SAEs, the accuracy of some explanations goes close to random, to 50%. Here it's not actually random because non-activating examples are much more frequent. So having a 50% accuracy is higher than random. But you see that as you go to the lower activation quantiles, your explanations start becoming worse, which just means, or our interpretation of this result is that those lower activation quantiles are less, let's say, monosemantic, or show a bit more diversity than the higher activations. And in a perfect world, you get this line as flat as possible, which would just mean that the full distribution is as interpretable as the highest activating examples. And it's not exactly that we see with the skip transcoders. There's still a slope, but maybe you could argue that the slope is a bit less steep in the case of transcoders and transcoders. So they both have higher accuracy in general, or higher scores in general, but their full distribution of activations seems to be better described by a single explanation, which is, I think, something that you'd want your explanations to have. And yes, this article is very short. This table is just showing that this is not just a single thing that you see on Pythia. If you train skip transcoders on a larger model, Llama and Gamma, you again see the same thing. Both scores, the average scores of detection and fuzzing, are higher. Simulation, which I didn't talk above, is also higher. This is for the people that maybe are a bit more distrusting of fuzzing and detection. And the increase in cross-entropy loss is also lower for the skip transcoder, even for larger models. So it definitely is something, at least, and this is kind of what we are arguing on this article, is that if you're training SAEs on the MLP, you should probably train transcoders instead of SAEs. Even if you don't want to train a skip transcoder, just the transcoder is most of the times. What is most of the times the transcoder is both more interpretable and as a closer. It's close enough to the loss, to the increase in loss, that you'd probably want to do a transcoder. If you're not worried and you really want to reconstruct as much as you can, doing the skip transcoder is just even better. Increases the loss much less and is as interpretable, at least the decoder encoder part, as the transcoder. So one last thing, and then if people have more questions, I'll be glad to take them. I actually like this idea of showing how good SAEs are in this kind of auto interp versus cross entropy loss plot, instead of showing it on L0 versus cross entropy loss. I think that our current auto interp scores are still not good enough for me to say that this is the right way to do it and you should never do any other kind of comparison. I think that that's not true, and there's much things to do. But I think we are, if sparse autoencoders and transcoders, etc., are something that we want to keep improving, I think we should be both looking at the reconstruction loss and some kind of interpretability score instead of the reconstruction loss and a measure of sparsity, because as you can see here, we can actually decrease sparsity. So we go from 32, 64, 128. This one is 4 times less sparse than this one, but the interpretability score didn't change that much, while the cross entropy loss increase is significantly lower. You have to remember that the cross entropy loss increase is exponentially linked to the performance drop. So any small increase in loss means that the performance of the model is very affected. While 1 to 2% on interp scores, it's probably basically the same score. It's basically noise. And that was it for these 2 papers. I hope that I didn't go too fast and didn't confuse people. If you have questions, now it's the time.
Yeah, someone asked via the text chat if there is any resource to get a better understanding of the phasing detection and simulation metrics described in this paper.
Yeah. So the Bills et al. Neuron. So the normal, I think, explanation, like the default, I would say, resource is the one that I linked in chat, where OpenAI used GPT-4 to explain neurons in language models. Then Anthropic used basically the same technique and now I don't remember the link of the Anthropic blog post, but did the same thing for SAE features, latents, and sorry, I'm searching for a link and I'm very bad at speaking and typing. And then we introduced this idea of fuzzing and detection for SAEs. There's other scoring methods that we don't do and other people have proposed, like generation, where you ask a model to generate text that should activate, and then you measure how much it activates. We don't do it because like the two-step process feels like it is a bit less scalable, but it's a good test that probably accommodates a bit this problem that I was saying, that you're not measuring false positives with simulation, or you're measuring them much less, while you do measure them with fuzzing and detection, but maybe these have worse problems. So this thing that I linked is the best resource. We do cite it, but yeah.
Thanks so much. That's super helpful. These links are great.
Okay, so
Hi.
yeah,
Are you saying something?
Yes. So
yeah,
it seems to me that with the auto interp, like there is two things that are maybe, I don't know how hard it will be to separate them, which is figuring out how much of auto interp being bad is that our methods to generate explanations are bad versus the sparse encoders or transcoders are generating some latents that don't have clear explanations. And I'm curious if you have some take about how much it's the problem and what might be done, like what is missing for the explanations.
Yeah, so we've definitely are looking at ways to improve both the explanations. So I mean, I think there's multiple fronts where you can attack the problem. Just on the explanation side, imagining that the SAE is perfect. If you imagine that the SAE is perfect and it is interpretable, you can, one, use better models, either larger models. So instead of using Llama 70B like we did, you could maybe use Claude, or you could use R1 or O3 or whatever, and have them.
Like wait a year and see what models come out. Yeah.
And I think that if you do that, you'll be able to see some kind of, or what we see is some kind of plateau where Claude is not that much better than Llama, and it's definitely not going to make a 100% right explanation. And maybe O1 or whatever, all these thinking models would make even better explanations, but it feels like, at least what we tried, they're not closer to completely understanding the latents. And so I do think that the way that you'd measure if the problem is just the SAE or if it's the pipeline is that you do a bunch of scaling laws, where you scale how strong the model is, you train models, you try to give more information to the scorers, you try a bunch of different things. And if all the curves seem to saturate as you do the thing better, it probably means that the underlying issue is the SAE. and not the pipeline. I don't think that we have these scaling laws yet, for multiple reasons. That it's probably expensive. You have to think of a bunch of different scaling ways. So you can scale the model, you can scale the thinking time, you can add more information, you can do a bunch of things. And we haven't done this, but I do think that, and I feel like most people that have looked at a distribution of an SAE will know that, yeah, there's just some latents that a human cannot interpret. And so it would be hard to ask an LLM to find the pattern. And for sure that current SAEs, especially at the low end of the activation spectrum, are just too noisy. And you probably are not going to have an explanation that explains all, that covers all the ground. And so yeah, I agree with you that the problem is interlaced, and that we cannot untangle the two behaviors at the moment, but it's not an impossible problem to untangle. It's just that, yeah, it's expensive.
I guess maybe something could be done, but maybe the wouldn't work as well. Is like try to design some toy model that has, that where you like build the model yourself and know what the features are, but maybe then it will be very realistic and it will then and see if the explanations match. But maybe it just will then it will be too nice compared to the real models and not look that much like them. I guess you could also try reverse engineering some model in some other way. In the hard way, and then using that. But I don't know if we could do that even for this chess model or something. But yeah, I don't know.
I think especially for people that are looking for problems, looking at maybe tracer models or other kind of toy models that are so small that if you train an SAE on them, you still maybe have a couple thousand latents, maybe for sure less than million latents. And it's not that expensive out of pocket to try to do auto interp on them. And you could really see, okay, are SAEs just bad or not? And you could probably distinguish them just by looking as a human to the latents, because there are not that many. You're probably not going to look at all of them, but you're probably going to be able to have a sample that's big enough to say, okay, SAEs are not actually capturing the real world or the real underlying distribution. And we already know that because the reconstruction loss is so high that
I mean, I was
just a
more
single SAE is like you're not training the model.
I was thinking more if we keep making things like trust coders or some, better thing. When do we know we got something that is at least approximately perfect? Maybe we have something that works very well, but we can't figure it out because maybe it has high reconstruction loss, but we don't know if it's just picking some random things that are not very interpretable anyway because our auto interp methods don't work. And in that case, something that people could do to check that kind of thing is there are some more, first there is the Neil Landa's Grokking paper where he reverse engineered the modular addition model. Maybe that's too small and weird compared to the real language models, but it could be interesting if someone use train whatever the newest thing is on that and see what the features it gets are, because in that case we actually know how the model works. Or maybe more realistic example is Tegmark recently, the Tegmark his students released a paper where they reverse engineer how I think it was GPT-2 or something, I don't remember, those addition, and they found like something similar to the modular addition thing, and that's like an actual language model, and maybe you can focus on that and like have some sparse encoders train on the whole model and see if you can identify the latency, what the sparse encoders are, so knowing what the actual mechanism for addition in that model is.
I think that the thing is that we are at the point that even making circuits is complicated. So even if you, even without thinking about auto interp, like making the circuit at the correct, let's say, granularity, I don't think we are that good at it. And doing what you're saying, I think that the thing that breaks first is not auto interp. Like I think you're not even reaching auto interp.
I see.
But that, I mean, that the underlying thing that you're saying is true. So, for instance, Bart was talking, the one that a few weeks ago talked about matrioskas. He mentioned in the Mech Interp Slack that in his case, his matrioskas are getting bad auto interp scores, even though he thinks they are interpretable, because in his case, matrioskas, the latents interact more strongly than the normal SAEs because there's some kind of hierarchy, and so the explanations have a hierarchical structure which our current, like our pipeline, cannot take into account because we are looking at activations individually and not at what the, let's say, parent latents were firing on. And so he was saying, okay, maybe I did discover a better model than an SAEs, but if I did the same plot, this plot that I'm showing you, mine would be worse because they would have a better CE loss but a worse auto interp score, and that's why I'm not completely advocating for okay, everyone should be doing this plot because I don't think we have figured out auto interp, but I think not trying or the best that you do on auto interp is that you look at 5 latent activations and you say, okay, they look fine. I think that's not good. If there's no one else, I should be going. Next week, and I can talk to you about this, Victor, but I'll not be. I'll be at the conference, so.
That's fine. The week of Jason, right? I can record it.
Yes. So Jason as the author, so maybe you talk with him to make sure, like the times and all the things.
Don't worry. I'll talk with him about that.
Okay. Bye everyone. Thanks for coming.
Bye.
Bye.